Welcome to the second half of Lecture 1 of Module 7. We're continuing to cover angular momentum, and in this lecture we're going to discover how we find their eigenstates. So we first have to start with the raising and lowering operators in angular momentum, and just like with spin, we're going to introduce those in exactly the same fashion. So the raising operator is Lx plus I Ly. L minus, the lowering operator, is Lx minus I Ly. If you recall, this is exactly what we did with spin. And then because the commutation relations of angular momentum are exactly the same as the commutation relations of spin, we've already gone through the following exercise. And we know that the commutation relations, when written in terms of Lz and the raising and lowering operators, are the following. Lz commutator with L plus minus is equal to plus or minus h bar L plus minus, and L plus commutator with L minus is 2 h bar Lz. And if you don't remember exactly how we did that, I encourage you to pause the video, write out the results in terms of the Cartesian commutators. You have L plus and L minus written in terms of the Cartesian operators. Just use those Cartesian commutation relations and verify these particular commutation relations, which are the commutation relations of the standard SU2 algebra. Okay, it's very important that you are confident that the commutation relation between the raising and lowering operators and Lz are as given on this page, because we're going to be using them in the remainder of this lecture. All right, let's start with working out the eigenstates and the quantum numbers. Now, since each Cartesian component commutes with the total squared angular momentum, that was something we established in the first lecture, but each Cartesian component does not commute with each other, the maximal number of commuting operators is 2. We take the total squared angular momentum and we take one of those Cartesian components. Now, it is standard to take the z component of spin as the one Cartesian component and then the total angular momentum squared as the other quantum operator. That gives us 2 quantum numbers, one corresponding to the eigenvalue of the total squared angular momentum. That eigenvalue we're representing with L, but I'm going to tell you exactly what that eigenvalue is in just a second. And the other one is represented with M, and that is corresponds to the eigenvalue under Lz. So if we look at these two equations below, we see the eigenvalue relationship is that L squared acting on this state Lm gives us h bar squared L times L plus 1 times that state. Again, that's a number times the state. It's an eigenvalue eigenvector relationship. And then for the z component of spin, it's Lz acting on this state gives me h bar times m. Now, we call L the quantum number associated with the squared angular momentum, and m is associated with Lz. And you note that this choice looks very odd, h bar squared L times L plus 1. You're going to see why we chose that as we go through the algebra. But for now, you could simply be confident in the sense that it can represent any positive number can be represented by h bar squared times L plus 1. And we know the eigenvalue of L squared acting on the state is positive because it's the sum of the squares of Hermitian operators. And the squares of Hermitian operators, because I can write them in an O dagger O form, they're always having positive eigenvalues. And so the eigenvalues of the sum of 3 squares of Hermitian operators must also be positive, or non-negative would be the correct term. And so this form is completely general, although I'll admit at this stage it does look a little bit odd. And I'm putting it in this form to save us some complications in trying to rework through our calculations a little bit later, because this is the preferred form that we want to keep it in. So I'm using 20/20 hindsight, and there's no way that you could guess that ahead of time. All right? Let's go on. So what we're going to do is we're going to determine both these values L and M solely from the algebra of the operators. And because that algebra of the operators came from the canonical commutation relation, as you recall from the first half of the lecture, everything that I'm talking about here is simply following as a consequence of the canonical commutation relations, which is pretty amazing when you think about it. All right, let's look at the raising operator. our first step is to show that L plus raises the eigenvalue with respect to LZ by 1. And what we mean by that is when L plus acts on the state Lm, it will be proportional to the state Lm plus 1. How do we verify that? Well, we determine what the eigenvalue is under LZ by operating LZ onto the state. So I need to operate LZ onto this state, L plus acting on Lm. And I've used parentheses here to emphasize that the LZ is acting on this state. And of course, they're operators. So we can just write that as LZ operated after L plus on the state Lm. And now we're going to use our algebra, okay? We're going to do the add zero trick. I'm going to add and subtract L plus LZ. I'm going to add and subtract L plus LZ. That's going to give me L plus LZ acting on Lm plus the commutator of LZ with L plus acting on Lm. Now, that commutator, we know what it is from the fundamental commutation relations of SU2. It's just h bar times L plus. And LZ acting on Lm, it's an eigenstate under LZ. So that's going to give me an h bar m. And now I'm going to collect my terms. You see I have a h bar m plus h bar. I can factor an h bar out. It's h bar times m plus 1. And now look at what we have. We have LZ acting on the state L plus Lm is equal to h bar times m plus 1 multiplying the state L plus Lm. That's an eigenvalue-eigenvector relationship with an eigenvalue of h bar m plus 1. And that tells me that that state is proportional to the state L m plus 1. So that does it. We're finished with that relationship. Now, the raising operator is increasing the eigenvalue m by 1 each time the raising operator is applied to the state. And that's why we call it a raising operator. Now, pause the video and verify that the lowering operator will lower the eigenvalue m by 1 each time we apply the lowering operator to the state Lm. Now, the only difference in the derivation is going to come from the minus sign that you get in the commutator of LZ with L minus is minus h bar times L minus. Otherwise, you can follow exactly the steps that we just did. And if you're having trouble, I encourage you to rewind this by about 2 minutes or so and go rewatch the derivation that we did so that you can do it for L minus. It's really important that you do pause the video here and go through this algebra because you need to be able to do these kinds of calculations yourself, and this is very important practice for you. So let's pause the video now. Okay, thank you for pausing the video and for verifying that algebra. We're now ready to move on. I just want to emphasize that because these operators, L plus and L minus, march us up and down the spectrum with respect to LZ, the L plus raising us by 1 each step, and the L minus lowering us by 1 with each step. That's why we call them ladder operators, because they go up and down like a ladder goes up and down. And each of the eigenstates you can think of as the different rungs on the ladder. All right, now we have to consider something that's very important that I already alluded to earlier at the beginning of the lecture on positivity. And we're going to use positivity to determine some constraints on these eigenvalues and how the L eigenvalues are related to the M eigenvalues. So first recall that Lx squared plus Ly squared can be written as 1/2 L plus L minus plus L minus L plus. This is an identity that we worked out with the spin operators, and again, because the algebra is exactly the same, it immediately translates to the angular momentum operators. If you don't remember it, just substitute in the definitions of the ladder operators in terms of the Cartesians and compute this. And you do have to worry about the operator ordering, and so you have to carefully work that out, but you should be able to get that the two come out to be exactly the same. Okay, so because we can write it as an L plus L minus, and because L plus is the dagger of L minus, then we know that the expectation value of Lx squared plus Ly squared is always greater than or equal to 0. And I'm going to just show you why that happens. The expectation value of an L plus L minus, because I can write that as an L plus L minus dagger, and then I can see that that's actually the norm of L minus acting on the state Lm. that norm squared must be greater than or equal to 0, and similar for them in the opposite order. And so when I add two non-negative numbers, I get a non-negative number. So that sum is also non-negative. Okay, but here's a really important identity. I can write Lx squared plus Ly squared as the total squared angular momentum minus Lz squared. Now, we know what the eigenvalues are of the total angular momentum squared, n of Lz, so we can, and we know that Lm bra multiplying Lm ket, that inner product, is equal to 1 because they're normalized states. And so you can just pull out h bar squared times L plus 1. That's the eigenvalue when the L squared acts on the state Lm, minus m squared, which is the eigenvalue that we're getting when the Lz acts twice on the Lm state. That must be greater than or equal to 0. Well, now that tells us then that m is less than or equal to the square root of L times L plus 1. And that means that there's a maximal m. We're going to call that maximal m sub max. And there's similarly a minimal m, because I can't lower below some lower number. Otherwise, the square of that number is going to get to be too large. We'll call the minimal one m sub min. Okay, so positivity has told us that the m eigenvalue has a maximum and a minimum value to it. Now, because I can no longer raise the operator, I must annihilate the eigenfunction when I apply an L plus on Lm max. And similarly, when I apply an L minus on Lm min. Please be sure that you understand how this works. We verified that the eigenvalue, if it doesn't annihilate it, it must give us an eigenvalue that is mmax plus 1 when I apply an L plus onto it. But we know that can't occur because mmax is the biggest one. And so we must have that the L plus annihilates this state. Okay, so we cannot raise above the maximum or lower below the minimum. And remember now, we have an operator acting on a state as annihilating the state. And as you recall, whenever we find that, it's really golden. We can use that to then determine eigenvalues and eigenvectors and all sorts of things. And we're going to do that next. All right, so let's look at first determining what mmax is. So we know L plus acting on this state is 0. If I apply L minus onto that, L minus acting on 0 is 0, and so it's still 0. But now I can rewrite that L minus L plus in terms of the square of the angular momentum. And so we can write that as L squared minus Lz squared. Remember, that is equal to Lx squared plus Ly squared, which I can write as 1/2 L plus L minus plus L minus L plus. And if I add this commutator, 1/2 the commutator of L minus with L plus, it cancels the L plus L minus term, and it doubles the L minus L plus term, so it's equal to L minus L plus. If that went too fast, please pause the video and verify that algebra. It's important that you understand where this comes from. This is an operator identity, so it's completely ironclad that this is true. Now, we can evaluate that commutator. It's just equal to minus Lz. And now we can operate these onto the state because this state is an eigenfunction both of L squared and of Lz squared. So we can substitute that in, and we get h bar squared times L plus 1 minus m max squared minus m max is equal to 0. That's a quadratic equation. We can solve the quadratic equation, and you find two roots. You find either m max is equal to L or m max is equal to minus L minus 1. We don't know which one it is yet, and we're going to determine which one it is right after the next page. And so what we're going to do on the next page is we're going to just repeat this thing for m min. For m min, L minus acting on the state is 0, so we operate an L plus on that. We work out the corresponding identity in terms of the square of the angular momentum and adding 0. And here we get L squared minus Lz squared plus 1/2 the commutator of L plus with L minus. That's the opposite sign of what we had before. We now can replace that with an Lz by working out the commutator. And now we have an eigenfunction relationship. We can just evaluate those operators acting on the state. We get h bar squared L times L plus 1 minus m min squared plus m min. Quadratic equation, we solve for m min. And what we find is it's either equal to L plus 1 or it's equal to minus L. Now, we only have to observe the fact that m min must be less than m max. And there's only one solution to these two equations using the fact that m max is bigger than m min. and that corresponds to mmax equals L and mmin is equal to minus L. So we've now determined mmax and mmin through this exercise. And we've also verified that these maximal and minimal values are related to the eigenvalue with respect to the L squared. This shouldn't come as a surprise, but it's pretty neat that we can just work this out and get this exact result. All right, now I'm going to show you that the quantum number L is either an integer or a half-odd integer. And to do that, we note that we've already established that mmax is equal to L and mmin is equal to minus L. So the difference between those is equal to 2L. Now, let's investigate how to transform from Lmmin to Lmmax. We know that every time we hit it with an L plus, we're going to raise the value of mmin by 1. And so if I hit it 2L times, I'm going to convert L comma mmin to L comma mmax. Now, we have to apply it 2L times to do that because the difference between mmax and mmin is equal to 2L. But I'm applying it an integer number of times. I can only apply this operator an integer number of times. That means 2L must be an integer. And if 2L is an integer, that means either L is an integer or L is a half-odd integer. And so that's how we establish that L is either an integer or a half-odd integer. It's going to turn out for orbital angular momentum, we must have L is an integer. That is not obvious, but if L is an integer, that also means that M is an integer as well. And the proof for this, that this is so for orbital angular momentum, is one of the problems you're going to be working on in the problem set. Note this is not true for spin. Spin can have half-odd integer values. And so it's only when the angular momentum is written in the form of r cross p are we restricted to only having integer values allowed for L. In general, with angular momentum, we can have integer or half-odd integer values. All right, now we need to work out the normalization factors. We require the angular momentum states to be orthonormal, and so the overlap of Lm with L prime M prime, we're going to take that to equal delta L prime delta MM prime. So we're going to set L plus acting on the state Lm to equal a constant CLm times Lm plus 1. We already established that it was proportional to the state Lm plus 1. And now we're going to just define what that constant of proportionality is. We're going to call it CLm. And now what we do is we just look at the norm of that state. That norm of that state is an L plus dagger, L plus. L plus dagger is equal to L minus, so I get an L minus L plus. Now we recognize that we can rewrite that L minus L plus just like we did before as L squared minus LZ squared plus 1/2, the commutator of L minus L plus. We recognize we can rewrite that commutator in terms of LZ. Now I have an eigenvalue eigenvector relationship, so I can extract those as numbers. I get L times L plus 1 minus M squared minus M. And so we now have established that CLM squared is equal to H bar squared L times L plus 1 minus M times M plus 1. And so we take the square root, and now the next exercise, or the next form that I write it in, you really should go through and verify that this is true. No one writes it in the form that we've written it down here, even though that's what naturally comes out of the algebra. We instead write it in the following form. And my claim to you is that these two forms are exactly the same, but you need to go through the algebra and verify that they really are the same. It is not completely obvious just by looking at them that this ends up being the same, unless you're really an expert in factoring. Okay? So we're going to set L minus acting on an LM to equal C prime LM, L M minus 1. And now we proceed through the exact same strategy that we used before. We calculate the norm. We rewrite it in terms of the operators. We act the operators on those states. They give us eigenvalues. And what you get after you evaluate those eigenvalues, we take the square root. And then we recognize that we do this factoring. And we get in the end that C prime LM is equal to H bar square root of L plus M times L plus 1 minus M. Now, what you should recognize is that this term has an L plus M in it. So if I evaluate C prime L minus L, I get 0. And similarly, the CLM had an L minus M factor in it. So if I evaluate that at M equals L, I get 0 as well, as we must, because we cannot raise the maximum value and we cannot lower the minimum value. And so these coefficients satisfy that. And that's one of the reasons why people like writing it in that lower form. because we can immediately verify this. All right, now let's construct the eigenstates. As we know, we just do that by applying the L pluses onto it. But now we know the normalization factors, so we can get exact results for all of the eigenstates by applying the raising operator onto what we call the lowest weight state, which is the state with the minimum L. And so the state with minus L plus 1, I just apply L plus divided by the number that will give me the correct normalization constant. I have to divide by an h bar, square root of 2L times 1. I do the same thing for L minus L plus 2. I just operate L plus over h bar one more time and divide by the normalization factor. If I do that a third time, I again apply the L plus one more time and divide by a factor. I can now do this k times, and you see we're starting to get a pattern. I'm getting a k factorial in the denominator, and I'm getting a 2L all the way multiplied out to 2L minus k plus 1. We can rewrite this in general in terms of factorial operators, factorial functions. And what we're going to do is we're going to replace k by L plus m. That then gives us the state L comma m. And we find the normalization factor is square root of L minus m factorial divided by 2L factorial times L plus m factorial multiplied by L plus over h bar raised to the L plus m factor, or m plus m power acting on L minus L. And then that gives us the states. So we have now solved another quantum problem. This one involved simultaneous eigenstates. So we simultaneously diagonalized both in terms of L squared and Lz. We found the eigenvalues and the states themselves, and we did this all just with algebra. And I hope that you're convinced that we really have a very powerful technique here. And as long as we can manage both the abstraction and the ability to work with this algebra, which you really will become much better with practice. So please, I encourage you, if you didn't do it, to go back and find those places where I asked you to pause and verify the algebra and go through and verify the algebra. And you will then get much more proficient with working with these operators and working with how we get these eigenstates. Let's now summarize exactly what we've gotten. For each L, we have 2L plus 1 of these states because m ranges from minus L to L. The states satisfy L squared acting on Lm is h bar squared L times L plus 1 acting on Lm, and Lz acting on Lm is h bar m times Lm. We have that L is either an integer or a half-odd integer. We know, however, that it's an integer if we're working with orbital angular momentum. That's when angular momentum is written as R operator cross P operator. Furthermore, we've determined what the states are. We also have the relations between the raising and the lowering operator. We know exactly what L plus is when it acts on the state Lm. And we know that we cannot raise past the maximum or lower below the minimum. And we have complex names that we have given these. L equals 0, it has one state, we call it a singlet. L equals 2, 1/2 has two states, we call it a doublet. L equals 1 has 3 states, we call it a triplet. L equals 3/2 has 4 states, we call it a quartet. L equals 2 has 5 states, we call it a quintet. Yeah, I was being a little sarcastic when I said we have complex names for these, but you will hear those names often when people are talking about angular momentum: singlets, doublets, triplets, etc. So it's good that you get used to exactly what those names mean. And now that ends the second half of Lecture 1 of Module 7.